Hi, in this video, I'm going to discuss chapter 24, magnetism, and we're going to discuss magnetic domains. So in the previous video, we saw that iron filings aligned with magnetic field lines. That's why we could visualize how the magnetic field lines are actually produced by those bar magnets. And we say the source of a magnet is north-seeking pole and a south-seeking pole, but it doesn't seem, maybe still not 100%, right? All the substance materials are made of atoms, we learned. And inside the atoms, there is nucleus. Inside the nucleus are made of protons and neutrons. And around the nucleus, there's electrons. That's what we know about atom. These electrons around it are constantly in motion, and they're constantly revolving around the nucleus, just like how Earth is rotating around the sun. So this electrons is constantly rotating around the nucleus, and also these electrons are spinning, just like Earth spins, rotates 24 hours a day. So it spins and rotates around. And this motion of electrons, motion of electric charge is producing magnetism. Let me show you in whiteboard. Here. Oops, sorry. Chapter 24, and this one is about magnetic domains. So we know that all the substance is made of atom, and electrons are in the atom, and these electrons in atoms are in constant motion. And what kind of motion it has is it spins and revolves. It has a spin and revolution. Around the revolution is around the nucleus. So when this motion contributes north and south, so when the electron is going around the nucleus, creates some kind of a north and south, right? North and south. But actually, the spin of electron is actually produces a bigger contribution to the magnetism. Spin. North and south. So when the electron spins around, it produces magnetic field. Spin is the main contribution. Let me see. This picture might be better. But what happens? So, but we don't just have a one electron. Typically, hydrogen has a one electrons, but a lot of atoms comes with the different electrons. And this spin of up and down, you might have a spin up, you might have a spin down. So when you have a spin up and down, north and south, they cancel out. So overall, you don't have any magnetism. But some of them, up and down and down and up, and they have several unpaired electron spins. Then you have some kind of magnetism. And some materials, so most of them, these magnetic field, electron spin, because the electron spin, sorry, because electron spin, should say electron spin, usually come in pair. Up, I'm sorry, up and down. So therefore, magnetic field cancel out. Elections, you don't just have a one electrons, and these up and down cancels out. So not all the materials are magnets. They don't have the magnetic field. But some materials, that's called ferromagnetic material. Okay, very important. Ferromagnetic elements. And these have several unpaired electrons. With same spin, line up. And these ferromagnetic material, just memorize it, okay? You should know this. There are iron, nickel, and cobalt. Iron, nickel, cobalt. These are the ferromagnetic material that has the unpaired electrons, and they have magnetic domains, okay? Which I'm going to explain what magnetic domain is. Okay, let me show you. Okay, so they do have some unpaired electrons. So then you have some north and south left over. However, right, you know, it's very hard to have a substance material. You don't just have a few electrons, few atoms to make the materials. You have so many electrons, atoms to have the substance, right? atoms are very, very small. So you have so many numbers of atoms. So typically, you do have unpaired electrons, and they tend to align with each other. Once you have a north and south neighbor, all tend to align with each other. So you do have a north and south, but that's at the same time. It's not that everywhere. It's very hard to have everything that's all along in the same feel the same align up in the same direction. So instead, um, all these ferromagnetic materials have magnetic domains. So they have magnetic domains. Iron, nickel, cobalt. Ferromagnetic magnets have magnetic domains. What is magnetic domains? Um, so I mentioned that it's very hard to have a unpaired electrons as all line up. So once you have a one establishment of the, let's say, north and south that's pointing this way, all the neighboring atoms do have a north and south, but this is the region of that. And then around here, you might have another one that has the north and south pointed in this direction. So you have a region. So these are the magnetic domains in ferromagnetic material. So inside the ferromagnetic materials, we have, it's not going to be perfectly all aligned naturally. That's very hard to have. You can think about phase transition too. Um, let's say when you boil water in a pan, um, when you boil water in a pan, if it's perfect water that do not have any impurities, perfectly flat surface, it's very hard for water to be boiled. Even though you keep adding the energy to it, adding the heat, it's very hard for water to become to boil. So what you do is that you on purposely put some defects in it. So like some pots, you could have like a zigzag, and then on those kinky defects points, that's where it tends to have a boiling start. So most of the materials do have not perfect um, thing. So you have a little bit of a defects here and there, and then when you have a phase transition type thing happens, it happens here, it happens here, it happens here, in a different locations. And over there, they feel the nearby forces, and then they align with each other. But since it could be happening rather simultaneously, so you have a domains that magnetic domains that's pointing to this way, magnetic domains that pointing to this way and this way. So these are the magnetic domains inside ferromagnetic material, right? So, and without external external magnetic field, these domains random, randomly aligned. So what happens? You put this ferromagnetic material in an external magnetic field. So initially, this iron, this is non-magnetized. Pointing to this way, has the magnetic randomly, I should point in this way, randomly pointing magnetic domains. But let's say I put the magnet bars nearby, then these magnetic domains, each one of them, they feel this external magnetic field. Then they sort of starting to align. So aligned like this. And then when you make it even bigger magnet, in a stronger magnetic field, external. Then they completely align. They feel the magnetic, because they have the magnetic domains. So when they don't have an external magnetic field, they're just randomly pointed, randomly aligned, so they're not magnetized, right? The nails that you typically you have that iron inside, they're not magnetized. They're just regular nail, except when you bring the bar magnet nearby, or that you saw those iron filings with the inside magnet. Then they feel the external magnetic field, so that there's those magnetic domains in the ferromagnetic material. They tend to align along the external magnetic field, and they themselves become magnet. So they become a temporary magnet. Once you remove the bar external magnetic field though, once you remove it, you have a kinetic energy. It has a temperature. So these magnetic domains goes back and then become randomly aligned. And then you put it in a magnetic field, they align. You put without the magnetic field, because of those jiggliness, the kinetic energy, they kind of go back to the random alignment again. Then it's not going to be magnetized. You can magnetize, the ferromagnetic material can be magnetized. How do you magnetize this ferromagnetic material? You can just rub it against it, stroke it. You can stroke it like this, and then they'll be magnetized. Or you can leave it in a strong magnetic field for a long time. You can also magnetize it. You train it to be in that direction. You force it, and then even with the higher temperature, in a room temperature, they stay. They can hold that, and they become a permanent magnet by stroking or put it in a strong magnetic field for a long time. So ferromagnetic materials, iron, nickel, cobalt, are the materials that has the magnetic domains, and they can become a permanent magnet. And when they're not even a permanent magnet, they can act like a temporary magnet. Once they're in, even though they themselves are not magnetized, they can be magnetized with the external magnetic field. So imagine that when you have a magnet though, permanent magnet, when you drop it, do you think that magnet will be stronger magnet or stays the same or become weaker? Or the permanent magnet, put it in a higher temperature, what happens to those permanent magnet? Is it preferable for permanent magnet to be stored in high temperature, or low temperature is better? No, right? If you drop the permanent magnet, you apply, you do work to it, and the potential, the kinetic energy converts into the energy to do a work inside to break the structure inside. So you give the energy, and then it tends to break those randomize again those magnetic domains, so it becomes weaker magnet. Also, when you put it in a higher temperature, you apply the kinetic energy, so that those magnetic domains tend to not align it becomes more random, so it becomes a weaker magnet. Hope, and there are other than the ferromagnetic material, there are other kind of possibly other kind of magnetic material, like you might have heard of paramagnetic material and things. They're just weaker. They do not tend to retain any magnetization as much for the paramagnetic material, but they do have unpaired electrons. You might have heard of rare earth magnets. Yes, they can become a permanent magnet, like irons, cobalts, and nickels. They can become a permanent magnet, but they don't become a permanent magnet above the certain temperature. You see, the temperature is important. So in a room temperature, they don't become permanent magnet, but they can be compound, form a compound with iron, nickel, or cobalt. So most of the rare earth magnets are actually a compounds with iron, nickels, and cobalt, and that's what makes the rare earth magnets. Okay, I'll show you the slide here that has a very good illustration of what I just talked about. Let's see. So here, magnetic fields. How the magnetic field is produced is always the motion of electrons, right? Or charge. So when you have electrons that's not moving, you don't have any magnetic field produced. Because the electrons in an atom are constantly in motion, they have a spin and revolution, and this spin contributes the magnetic field. So you do have some magnetic field produced due to the electron spins. However, these electron spins tend to come in pair, and most of the material have this magnetic field cancel out. So they don't have any magnetic field produced due to the spin. But only ferromagnetic material, nickel, cobalt, iron, have the unpaired electron spins, and they form magnetic domains. So those ferromagnetic materials have the region of the electron spins that's aligned with each other that has the magnetic field that's produced. But typically, these ferromagnetic materials, the magnetic domains are still randomly pointed, right? And only when you put it into the external magnetic field, then these unmagnetized iron, magnetized, so randomly aligned magnetic domains starting to align along the external magnetic field. And then if you put it in even a stronger external magnetic field, they tend to align very well. So they become a stronger magnets. And that's why when you cut into a smaller and smaller pieces, because of that, it's the motion, the spin of the electrons, they're creating north and south. So they always come with the north and south. You cannot just extract out north or south by itself. Okay. So what makes the difference between a temporary magnet like iron, those nails with the iron bits inside? They have a magnetic domains, but these magnetic domains are only aligned in the external magnetic field. Once you remove from the external magnetic field, then this alignment of the domains returns to the random arrangement. So they won't become magnetized again. But permanent magnet can sustain its alignment even they're removed from the external magnetic field. Okay. How to make the permanent magnets? It's by placing a piece of iron or this ferromagnetic material in a strong magnetic field, or you can stroke those nails or needles that has iron bits with the magnet. And you align the magnetic domains by stroking it. Let me share you another video. So here is another video that I like to share. This one. Okay, here. Avery, what are these?
This?
Nope, these things.
Nails?
Nails, just regular nails. Just put it there. It doesn't do anything, right? Can you use this magnet? Sticks.
Do you have iron bits?
Yeah, exactly. Inside a nail, there are irons in it. So nail has irons. That's why it feels those external magnets, magnetic field by the magnet, bar magnet, and then it gets attracted, right? Let's see the other one. So how about this one? And what do we have now on
A spoon.
a spoon? Okay, stainless steel spoon. Can you try and use the magnet? It's metal. This is a metal. Are you sure you're doing a good job? Yeah. Let's put the nails. Okay. Do the same thing again, please. Thank you. You see, nails, sticks. But not the spoon.
Yep.
Yep. Yep. So people do tend to confuse with them. All the metals are can be magnetized. No, no, no. Ferromagnetic material, only irons, nickels, and cobalts. They have a magnetic domains. Therefore, they can feel the magnetic force. Other kind of metal, even though it's metal, they're not going to be magnetized. They don't have magnetic domains. Stainless steel is not ferromagnetic material. Aluminum, can you attract the aluminum with the magnet? No. Gold? No. You see? The ferromagnetic material. So don't get confused just because it's metal. And yes, true, something to do with the electrons, but it's completely different. It's the motion, the spin of the electrons that produces magnetic field. All right? Okay, so that's what I wanted to discuss in this video for magnetic domains. And then I guess I'll see you in a discussion.